One last kind of example problem for the section. We are going to use either a linearization or a differential to approximate the square root of 100.5. Now we have complete creative control over this one. We can decide the function and we can decide where we're going to set up a linear approximation. My recommendation would be to make sure that you're dealing with a square root function and pick a perfect square that's close to 100.5. So I think what we're going to do is use f of x is equal to the square root of x, and we're going to go with x equals 100. Now if we wanted to go linearization, then we would set this up as the linearization of x is going to be equal to f of a, which in this case would be 100, times f prime of a times x minus a. So this is where 100 would be the perceived a value. Now with that in mind, if we do f of 100, this will be equal to the square root of 100, which would be equal to 10. For the first derivative, we would treat this as the derivative with respect to x of x raised to the 1/2 power. Applying the power rule would give us 1/2 x to the negative 1/2 power. Finding this derivative, evaluated at 100, is going to be equal to half of 100 to the negative 1 power, or negative 1/2 power. Negative means put it in the denominator. Half means square root, so this would be 1/10 times 1/2. So 1/2 times 1/10, also known as 1/20. So our linearization is going to look like the following. The linearization is equal to f of a, which is 10, plus 1/20 times x minus 100. So near x equals 100, the interpretation of this is that the square root of x will be approximately equal to 10 plus 1/20 of x minus 100. Let's go ahead and plug in that value of x that we're using. So we'll plug in x equals 100.5. So in the interpretation, this means that the square root of 100.5 would be approximately equal to 10 plus 1/20 of 100.5 minus 100. Then we can go ahead and simplify this expression. Going according to the order of operations, 100.5 minus 100 would be 0.5. This is saying take half of 1/20. Let's turn the 1/20 into a decimal though. So 10 plus 0.05 times 0.5. This is saying half of 1/20. This will be 10 plus 0.025, or a final answer of 10.025. Now if we wanted to use a differential for this, we would start by setting up the fact that dy is going to be equal to f prime of x times dx. We've actually already done most of the legwork on this, so we might as well make use of it. Our derivative was equal to 1/2 of x time, 1/2 of x to the negative 1/2 power. So half of x raised to the negative 1/2 power times dx. Now since we're going from 100 to 100.5, the dx in this case, or delta x in this case, would once again be 100.5 minus 100, which would be equal to 0.5. You'll notice though that that calculation did come up in the linearization as well. So plugging in the things that we know, this will be half of 100 to the negative 1/2 power times 0.5. In fact, everything that you see right here is the exact same thing as what we did right back here. So the 1/20 came from 1/2 of 1/10, which is what we have here, and then we multiply by 0.5. This lets us know that the change in y moving from point to point is going to be the same thing as what we did before. To get the actual value, we would add that to the original value of y. So f of 100 was equal to the square root of 100, which was equal to 10. So that means that f of 100.5 is going to be approximately equal to the y value that we started with, plus whatever the change in y was, giving us once again 10.025. Now I predict that that's going to be slightly larger than the square root of 100.5, but let's take a look. Taking the square root of 100.5, we were anticipating 10.025, and I see that we got 10.024968. I would say we did quite well with our approximation on this one.